So let's go to the question on why we would like to have competition. And basically what we're now going to do is review material that is in MOTAS chapter 2, and which should, for the most part should be known, which is answering the question of, what is it that competition does that is worth protecting. So the idea is what we want competition to achieve is efficiency in particular. So efficiency, we can divide it up, distinguish here different parts to that, different aspects of that. So the first part is allocative efficiency. The second one that I'll discuss is productive efficiency, and then we'll go to dynamic efficiency. So what are those again? So if you remember, allocative efficiency basically means, do those players in the market that value products the most, do they in the end get this? Do goods, do resources, scarce resources get allocated to those who value them the most? And what it amounts to is, the question is indeed for given costs and demand is indeed total surplus, is that maximized? So you remember, of course, total surplus, in the simple one product graph, it's a supply demand graph. A total surplus is just the area that's colored in here, so we're consisting of the consumer surplus on top there, CS, and the producer surplus, the blue area. And you see that indeed whenever marginal cost is equal to demand, so we know then that that's what the competitive equilibrium is, and that actually maximizes that area. So what a monopolist instead, so somebody with market power, so without full competition, what a monopolist would do, it would restrict its quantity to the monopoly quantity and making price go up a little bit. So a monopoly quantity, of course, being related to the marginal revenues equaling marginal cost point here. So what you see is that this area, this colored area, of course, gets smaller here and also gets redistributed. And so there's money flowing, or surplus flowing from consumers to producers, as you know. But in particular, this gray area, which we call the deadweight loss, that measures basically the loss of allocative efficiency. So that's allocative efficiency that may actually be exacerbated a bit, or actually a lot, by rent seeking. So we have deadweight loss in the sense that with monopoly, not everybody gets what they need to be, but also we also saw these producer surpluses get larger as we go to monopoly, and that means when different agents or different firms might have the opportunity to become the monopolist, they will actually have an incentive to spend a lot of effort and cost into getting this monopoly. So these various agents in the market, various firms, might compete to become monopolists, and that's going to be costly because all these firms are going to exert the effort to get there. So it might be lobbying, or they might try to bend the rules in their favor, or they might just spend a lot of time on advertising and getting big, which might not be, which might lower total surplus, because the total effort, the total cost of effort that these companies together will be willing to spend might be as large as the monopoly profits. And we're going to look into a particular exercise in the tutorial that actually will formalize this, where you will compute this. So that's allocative efficiency. So let's then go to the next aspect of efficiency, which is productive efficiency. So the idea of productive efficiency is, are goods produced at the lowest possible cost? So what's the benefit of competition? Well, competition basically does two things. So on the one hand, competition is a great incentivizer, is an incentivizer to lower cost. So if you are a monopolist, you might be satisfied with your achievements and with your cost level, but if you're competing, on the other hand, you will be constantly be on edge to actually be a lower cost producer than your competitors, than your rivals. So that gives a lot of incentives indeed to lower costs and to make production more efficient in that way. And secondly, competition is also not only a great incentivizer, it is also a great selector. So this is more or less, if you wish, a Darwinian argument. So if there are many different firms, some of them which are high cost, some of which are low cost firms, well, competition succeeds in wheeling out all those high-cost firms, making sure only the low-cost firms will survive, that high-cost firms actually exiting the market. So again, that makes sure that total costs of producing are lowered by basically introducing competition. So those are again our arguments from productive efficiency for why we would like to have some degree of competition, because that's going to make production less costly, basically. So finally, and there's a more nuanced picture, we have dynamic efficiency. So dynamic efficiency that relates to innovation and long-term cost reduction or long-term quality improvement, for that matter as well, product development. So now we know actually that if you want firms to invest in bringing new products to the market or implementing innovations that increase quality or reduce costs, there needs to be some market power. We need those companies to have a price that they will want to attain, that they will want to spend effort and time for attaining in order to get to this achievement. And that's basically why we have a patent system. So if you get a patent, your achievement, your innovation is basically protected, which means you have a type of monopoly power for a while. So not forever, but for the duration of this patent. So patents convey market power, and this market power actually incentivizes firms to spend the effort and the money, the research efforts to indeed develop new products and bring those to the market. So the question is, of course, how much market power do we need? Do we need monopoly for that, or is there does full competition achieve effective and efficient investment in product development as well? Well, the truth usually is somewhere in between, right? There's a middle ground here. So in order to evaluate that in a little bit more detail, what we are going to do now is to have a look at a model of investments to reduce costs. And this model actually is from the book, from CompPol1.3 And so what is this model? Well, it's a model of cost reduction, investment to reduce your costs in a Kuno setting, so in a quantity setting. And the idea is, let's suppose we have n different firms, so n can be any positive whole number, and if n is 1, then we have monopoly. If n is high, we have a more competitive situation, and we are considering a two-stage game. So in the first stage of this game, each firm will invest. So I'm going to index these firms by the index I. So each of these firms I will have the ability to invest to lower their costs. So they will all start out from the same cost, actually from C, but they can invest to reduce their costs to C minus XI. But of course, it's costly. There's some investment costs which are, as depicted here, a half times G, which is some parameter, some cost parameter, times this X, this cost reduction squared. So that happens in the first stage. Each of these firms is going to select their particular X. And then in the second stage, each of these firms will have their lowered cost, and they will then engage with these potentially different cost levels into Kuno competition. So how do we solve such a game theoretic model? It's a two-stage model, and basically what we want to do, we're going to solve this model by backward induction. So first of all, we're taking as given some configuration of all these different X's, so they might be different for different firms, and we ask, in the Kuno equilibrium, that then the different cost, with the asymmetric cost, what are then each firm's profits, depending on this combination of those different levels of cost reduction X for each of these firms. And when we know that those profits in the second stage, we can then step back, do the backward induction, go to the first stage and see what are the incentives of these firms to invest in their cost reduction levels X, and in other words, then finally, what's the Nash equilibrium for those investments in X. And well, once we know that, we can evaluate, what's the welfare consequences of that level of investment in cost reduction and subsequent Kuno competition in that market. So what is this model going to look like? Well, we take our favorite, one of our favorite, most simple demand models, namely linear demand. So price in this homogeneous good market is just some cutoff price, A basically, minus the sum of all the quantities that will be produced by all these different companies. So the J again here ranges over all the different indices from 1 to n, so all the different firms, I should say, from 1 to n. So Qj will be the quantity produced by firm J in this setting. And the cost for firm I after this investment stage, or to look at stage 2, so the costs have now settled for each firm at its particular C minus xi. So again, C was the same for everybody, but these x's might have been chosen particularly off equilibrium. They might have been chosen differently by each firm. So C minus xi is a primarily different cost level, marginal cost level for each different firms. So then what we need to do is we need to find the equilibrium, the Cournot equilibrium in this second stage. So in order to do that, we have to write down the profits for each of these firms, which is just P minus their marginal cost being C minus xi for firm I, times the quantity Qi. And there we sort of substitute this expression for this linear demand, inverse demand rather, in the brackets over here. So what do we want to do? We want to solve for the Nash equilibrium in this Cournot competition game. So that means we want to solve for the first order conditions. So let me actually do that on paper to see how that works in more detail. So let me switch to paper here. So here on paper we have price. I already wrote that down. P equals this cutoff price A minus the sum of all total quantity that's produced in this market, and then we have to consider the profits of firm I in this market. Well, again, this was this price minus marginal cost times the quantity that this firm is going to produce, and if I then substitute that price, and here it's going to be A minus the sum of all these quantities minus those costs, right? C minus xi. So this J ranges over all firms from 1 to n, and this I is the particular firm that we are sort of currently considering, and we multiply this by the quantity that they are producing. So the first order condition, of course, is for that we have to take the derivative. The first order condition is this is 0. It's a Cournot game. So well, let's do that. Let's write it down. So of course there's a Qi over there, so that gives us the contribution minus C minus xi, but there's also a Qi in here, of course, a minus Qi even. So we have 1 minus 1, which is the derivative that's from here, multiplying this Qi over here by using the product rule. So this is firm I's first order condition. And of course we have the same similar first order condition for each of these i's, from I equals 1 to n, and of course a useful way to solve this system of these n equations, simultaneous equations, is to add them up. Because what happens then, so if n of these equations, one for each value of I, so adding those up will give us n times A minus n times the total quantity, the sum of all these Q's, minus n times C, plus now the sum of all the xi's. Let me again write this as xj's, because this index is just an index name for this. J is just the name for the index running from 1 to n, just like I. And minus the sum of all these quantities equals 0. And so this is what we get when adding this up. So what we want to do to achieve here is to solve for the sum of all quantities, or in other words, what the price will be, because that's what's going into this price. So well, that's going to be not too difficult, because we have here the n times the sum of all quantities, here 1 times the sum of all quantities. So taking that to the other side, we get, in fact, n plus 1 times the sum of all the total quantity in the market is equal to n times A minus n times C plus the sum of all these cost reductions. Okay. So that means, in other words, if we divide out by n plus 1, the sum of all these Qj's is going to be 1 over n plus 1 times this expression over here. So now that we have this, we can actually solve for what each individual firm's Qi is, because we know those satisfy their first order condition. So this is the first order equation that holds for these firms. So we now know what Qi is. So just plugging in the sigma Q that appears here, which is this expression. What do we get? The Qi is going to be, well, A minus n over n plus 1 times A. That gives us 1 over n plus 1 times A, and the same goes for C. So we have here A minus C divided by n plus 1 by combining these terms involving A and C, also with the A and C terms in this sum of all Q's. And what we still have to add to that is, of course, the sum of all these xj's, or rather the 1 over n plus 1 times that sum. So that's sitting in the sigma Q here, minus sigma xj divided by n plus 1, plus this xi that we have over here, right? So we have minus times minus xi, so this is plus xi. I'm going to write this as plus n times xi plus xi divided by n plus 1. So just to make sure that we have an n plus 1, the same n plus 1 in the denominator here. So if I then take that together, what we get is 1 over n plus 1 times A minus C. Now I'm going to combine these n times xi and the sigma xi as plus sigma xi minus xj, ranging over all j's, divided by n plus 1. So again, the sigma xj is what we have here, divided by n plus 1. The n times xi is just the sum over xi n times. They're n terms, but they're n the same terms. So each of these terms contributes 1 xi, they're n terms, so that gives us n times xi. And the only thing that I still need to have here is plus this xi. Plus xi. Divided by this n plus 1. So that's this final part over here. So this is what Qi is. So now what is pi I? Because that's what you are, the profits of this firm in the second stage, because that's ultimately what you're after. So what's each firm's profit in this Kuno stage? Well, pi I is, of course, what we have there, P minus C minus xi times Qi. But since Qi by the first order condition is actually P minus C minus xi, this is just the same as Qi squared in the equilibrium. So using the first order condition, we can write pi I in the equilibrium for each firm is the same as the square of the total quantity they will produce in this particular equilibrium. Okay, so this is Qi squared. This is the profits that they get in the second stage. So now we do the backward induction. So we go back one step. So that means we are now interested in the x and the profit. So basically in stage 1. So what do you get if you are in stage 1? Let me denote that with a capital pi, so big pi. So your initial profits up front is going to depend on, of course, the equilibrium values of all those q's, which in turn will depend on the choices of all those x's. So that is going to be your Qi squared as a function of your xi and, of course, of all the xj's chosen by your rivals, minus the cost actually of investing in cost reduction. And remember, this cost I chose to be quadratic. So cost is here 1/2 times g, which is cost parameter, times x squared, your xi squared. So what we can see from this, or what we can learn from this, basically is, of course, we can solve what the optimal xi will be, and it will be the same, so it will be symmetric equilibrium. But in order to gather some understanding, what we can look at is, what are your incentives basically to invest in your xi? So of course, one of the incentives is going to be costly, right? So if I invest in cost reduction, I'm going to incur these costs G times XI. So that's going to reduce my profits. But of course, I'm also going to increase my profits because the QI, so the profits here, QI, which were QI squared that I get in the second stage, those depend on QI, and QI in turn depends on your own XI. So how? Well, there's an XI over here, and there is n different XIs over here. So what we see is, first of all, we have the cost. So what are the cost of investing in XI, but we want to know what are the benefits of investing in cost reduction. And essentially, here we've split this up in two different benefits. On the one hand, we have a demand expansion effect. That's traditional. It's also known from monopoly. So if costs go down, then price will go down. And indeed, you will produce more. So QI is going up. And that's basically this effect here. So XI going up means the QI is going up. So if you invest in XI, you will invest in QI. And because profits is QI squared, that will also raise your profit. So how fast, or so how fast does your QI grow? So basically this demand expansion effect acts on QI as XI divided by n plus 1. So it goes as divided by n plus 1. 1 divided by n plus 1. So what you see here, if you increase XI, then you're increasing your QI, and by this demand expansion effect. Now, how fast does it go? Well, it goes faster as the lower n is. So particularly we see that for monopoly, this is where n equals 1, there's just one firm. This is going to have a huge effect, whereas this n is very large, well, it's almost going to be negligible because this 1 over n plus 1 is going to be a very small number. So you don't notice much of this demand expansion from your own investment in cost reduction. So this is greatest for monopoly. But this is only one contribution, so there's another contribution here for this XI, so there's n different terms, well actually n minus 1, because one of these is going to be 0, because when j actually equals I, this thing is going to be 0, so there's this other effect, let me call this the competitive effect. The competitive effect of wishing to outperform your rivals, to win over production from your rivals. So when does it happen? So when your X is bigger than those of your rivals, you are winning demand, so increasing your profits at the expense basically of your rivals who will have lower XJ. So what's the prefactor going in front of this one? Well, again, these are n different terms, where one of these terms is going to be 0, because the one where j equals I. So essentially the effect on QI, it affects QI as n minus 1 divided by n plus 1. So this is going to be greatest for n big, or n going to infinity, so to full competition. So the larger n is, so the more competition there is in this Kuno market, the larger the benefit that you get from this particular term, in the sense that there's more firms that you want to outperform and that you want to grab their market share from. So we see basically three contributions. With this demand expansion effect, which is biggest for monopolies, and they're expanding demand by lowering your cost. This competitive effect, you are also getting market share and therefore expanding your demand by stealing some of the market share of your rivals, and that effect is going to be largest. You want to increase X the most if n is fairly big. And finally, of course, is the cost. It has to be balanced against the cost of investing in cost reduction. So that's from this final contribution over here. Okay, so let's look at that again in the slide then. Here we are. So here's this particular QI, so again this the same expression that we saw. So you see this A minus your own marginal cost, but then plus these differences in marginal cost between the different firms, because that's going to reflect this business stealing effect basically among these different firms, divided by n plus 1, and total profits in the second stage being Q squared, QI squared. So in the first stage you are going to maximize, you choose your X basically to maximize your profits at the second stage, which is this one, QI squared, minus the cost of investing in cost reduction in the first place. And in the end, this will be the same for each player. So in the end, in the equilibrium, basically, this will be symmetric. So all n players will invest in the same amount of cost reduction. So we can then, for this particular equilibrium, we can compute that. And we can actually see, I mentioned this, of course, these different competing effects. So it's demand increase effect or appropriability effect, which is the biggest for the monopolist, and the other one, investing to be better than your competitors, which is going to be biggest when there's a lot of competition, and that has to be balanced against the marginal cost to invest. So we can compute welfare and actually plot that, and I advise you to actually try to reproduce this picture by computing the consumer surplus and the producer surplus for the different n's. So each n will give rise, so its choice of your number of firms will give rise to different choices, equilibrium values of X, and therefore also equilibrium values of the Q's that are going to be produced. And you can in fact then compute what's total consumer surplus and what's total consumer producer surplus for this, including the cost of this X, this cost reduction effort. And what you see here actually is for n very low, particularly n equals 1 monopoly, total welfare is not that big. But on the other hand, as n grows very large, we also don't reach the maximum. So we see for this particular example, this stylized example, the optimal amount of firms in terms of maximizing total welfare, total long-run welfare, so including the efforts to reduce costs by innovation, which was measured by this XI in our model, is going to maximize somewhere between 3 and 4, I guess. So that's basically those two competing effects at work. So what does competition policy do? Well, in this particular model, we can precisely compute how many firms there should be, because which number of firms is going to optimize welfare. Well, in practice, we cannot do that. So we cannot say, oh, we just want 3 or 4 firms in this market. That's going to be very hard, in particular, because we actually do not have sufficient information to do that typically as a regulator. So in a stylized model, we might know this, but in real life, actually, this is going to be way harder. And so what we rely on is we need to have some market power as a reward for investment. So we don't want to regulate to make sure that everybody is as competitive as possible. But there are limits to the degree of market power that we wish to allow. So of course, sometimes we are we might be closer to actual regulation of behavior, regulation of prices even, and that would be the case in which there's essentially a single monopoly that can capture the market, and this single monopoly that has control of perhaps one monopoly segment of the market. So you can think of a piece of infrastructure that's essential for everybody who wants to enter the market. So take electric power distribution. So if you want to sell electricity to end users, you will need to have access to the electricity network, which typically is a monopolist, and that will be regulated because there is just a single firm doing this. Also, that's a typical case in which we do have regulation, but in sort of more nuanced cases, for instance, in Microsoft, there has been in the early 2000s there were a lot of competition cases against Microsoft, in particular its the position of its Windows system, and indeed the EU there took a slightly more invasive view of what it should do with its competition power authority to do to Microsoft, and actually the EU mandated that Windows made available its source code, at least to sufficient effect that other program developers could actually write their programs in such a way that they dealt easily with the Windows operating system. And the EU went actually farther here than the US, where in the US basically the idea is sooner, or more than in the EU at least, well, if there is a monopoly, well, we also want to give these monopolies a chance, and we want to give other players a chance to bypass their monopoly by building their own systems, or their own infrastructure, or their own ports for importing goods into the country. Whereas the EU might say, well, the port of this particular port in Rotterdam, say, might be so important, we want to regulate, at least to mandate that this particular port will give access to other players that want to import goods by ship into the market. So there is of course also a case for having the market solving it, which might then be closer to the US philosophy here. So of course, to some extent, most markets are contestable. So it's sometimes sketched in the quote in the phrase, competition is one click away. So in the digital market, so if you want to switch away to a different browser, for instance, it's just one click or a few clicks at worst. But that sort of sometimes neglects switching costs, which might be substantial in the short run. So in the long run, this might work, but in the short run, you might then, it might take a while before competition actually kicks in. There might be barriers to entry, so other firms might have great difficulty, perhaps affect this difficulty being influenced by the monopolist who is already active in the market. There might be network effects or other natural monopoly aspects that make it difficult for firms to enter markets in the short run. So that makes it difficult to really claim that markets are contestable in the short run. But summarizing, in the end, basically the goal of competition policy is to protect the competitive process, so to make sure that other firms can enter the market, in particular if they are more efficient or have a higher quality, say, than the traditional firms, rather than just saying, well, this is what prices should be, or this is what the number of firms should be. So the goal of competition policy typically is to protect this competitive process, to make sure there's sufficient dynamic efficiency in the long run, balanced by sufficient static and productive and adaptive efficiency in the short run. So let's then go to actual case works. So the first part basically of a typical competition case is going to be the market definition part. So that's what we're going to look at in the next slides.